right, everybody. So here we are, another section of our science notes. And we are talking about proteins. Let's see, I got purple today. That sounds good. All right, so we're talking about proteins. Now that's all the way down here on your page. Okay. Introduction. Protein molecules are in all living tissues of plants and animals. That makes sense, right? Proteins are very strong. Okay, they have lots of different roles. We're getting into that. If you've ever heard of humans or Earth life being referred to as carbon-based life forms, this is some of where that comes from. Okay, proteins contain C, H, N, O, and S atoms. So what are we talking about here? Okay, we're talking about carbon, hydrogen, nitrogen, oxygen, and, believe it or not, sulfur. Okay? And they contain these specific types of atoms, but they may contain others as well. These are just some of the really, really common ones. Okay? Proteins have many roles in our bodies and in all living things. Hair, skin, and nails here. Okay? This protein, there it goes. This protein is called keratin. All right. Let's go on to our next thing here. All right. Chemical reactions, enzymes. One enzyme we've already talked about a little bit this week is amylase. Salivary amylase. Okay. Also, hemoglobin. Transport. Hemoglobin carries O2 or oxygen in blood. Heme here. Heme refers to iron. My bad, guys. Refers to iron, okay? And this is actually what makes your blood appear red. This is like when things rust, they turn to sort of an orangey reddish color. It's because that is the color of iron. All right. And so the hemoglobin, that bright oxygenated red blood that you think of, that is due to the iron groups and the heme groups in the hemoglobin. All right, motion. Muscles are made of proteins. This is huge, okay? I'm going to put exclamation points by that. Muscles are made of proteins. This is exactly how our entire body pretty much is put together. So, protein, pretty important, as well as eating protein, making sure you ingest enough protein to help your body either form new muscles or repair any damage that you might do just by using your muscles or working out even. Okay? All right. And also, proteins coordinate chemical activities. Insulin. Insulin is used, that is a protein that's used to help your body break down glucose constituent parts to where it can be used in the body for energy and other things. And when someone has a problem either making or using insulin, that's what we refer to as being diabetic or having diabetes. Okay? This right here, this is what we're talking about. All right. So here is the beginning of amino acids here. Let's see. Oh, yeah. There we go. All right. So let's talk about amino acids since we're going to clearly get into depth. What is an amino acid and why is it important? Why should we talk about it? What could we possibly need to know about that? All right. So, I know that you guys have already heard me talk about deoxyribonucleic acid, ribonucleic acid. I know you guys have heard me mention that already at a couple of different points in here. So, I want you to know that this is where it's going to start coming full circle. Okay? All right. So, let's just do a quick little kind of breakdown here. All right. Hold on just a second. I'm sorry. Technical difficulties. I know it sounded like I disappeared for just a second. All right. Give me 1 second. I'm having a little bit of technical difficulty. But I will have this brought over in just a second. Okay? All right. Now, proteins. That's what we're talking about right here. Why are amino acids a big deal? Why are amino acids important? Weren't we just talking about proteins? Okay, so if you guys were to kind of get a mental image about a Lego construction, okay? So let's say that your Lego construction is something that's sort of long and skinny, okay? So it's the belly of a starship, or it's a snake, or maybe it's a long sort of bridge even, or a strip of road or train track. Okay, so picture something long and skinny like that, okay? If proteins are a chain, okay? So if proteins are a chain like this, so they would have a link where they'd all kind of connect together, right? So if that's what a protein is, then each of these individual links or building blocks or Legos, however you want to think about it, these are your amino acids. Okay? So, remember how important we were talking about proteins were? Well, this right here is why amino acids are super important. Now, we have 20 different ones that we find in nature, and they all have a very specific general structure, and then obviously they veer off from that to become the individual 20 different amino acids. Ooh, excuse me. But they all can connect together to make these chains, to make these particular proteins, and they have to be in a certain amount and in a certain combination, a certain order, okay? So let's look at some of these on the next page. Okay, so hydrophobic, real quick, and hydrophilic, okay? We talked a little bit that hydro means water. Phobic, if someone has a phobia, that means they're scared, right? So if it's hydrophobic, that means it is scared of water, okay? It doesn't want to be around water. Whereas if it's hydrophilic, that means it loves water, okay? And that's obviously super important depending on which sort of environment it's going to be in. Will it actually work or not? Okay. So, Let's look at some of these. I'm going to change color. Methionine, valine, leucine, isoleucine, threonine, phenylalanine, tryptophan, lysine, histidine, and arginine. Okay, so we can synthesize those of the 20 that we need. We can synthesize about half of them, okay? So if you're looking back at this list, these 10 that are circled, these are called essential. Okay, these are the essential amino acids because we don't actually make these. We have to get them from our diet. Okay, and so it's not, unfortunately, uncommon for people to, when they have chronic disorders that affect the absorption or the utilization of amino acids, and therefore the proper making and use of their proteins, it's not uncommon for them to have a deficiency in finding one of these amino acids in their diet and then being able to use it properly. All right, let's go on. Okay, so let's talk about stringing them together. We've got a polypeptide here, and that's referring to these different bonds here, okay? Amino acids are held together. Oh, let me change my color back. Amino acids are held together by a peptide linkage, okay? This is referring to this specific type of bond, okay? Peptide linkage, peptide bond, is formed when these things are coming together and they lose a water molecule, okay? So if you look down here at this synthesis here, okay, they end up with 3 extra water molecules shed off the end, okay? This is how we know that they're bonding in this particular way. Okay, also worth noting is that proteins a lot of times exist in a 3-dimensional space. They exist in a 3-dimensional structure. And again, I bring up the idea of DNA, deoxyribonucleic acid, and RNA. All right? So we have several different ways to describe the structure. The first one that we use, the primary structure here, number 1, tells me the order that they're in, okay? They're all chained together. So here I have my picture. Oh, that was a very strange number 1. All right, so here I have my picture of everything in order, and this is showing me, okay, I have this that looks like the white circle, and then I have the green sort of rectangle, and then I have the red circle, and then I have another white circle, and then I have a green sort of T. And so it's showing me which ones are coming in which order. Okay, that's the primary structure. Step 1, what do we got to know? Then we kind of step back and look at the secondary structure. Okay, secondary structure is going to tell me whether it is called a helix or a sheet, okay? Otherwise known as, let me put it up here, alpha helix or beta sheet. Okay, now we know what a helix is, right? We've talked about DNA helixes before in class, and we've talked about, I'm sure you've heard that somewhere else, right? So this here, this secondary structure, number 2, this would obviously be a helix, right? Because it's kind of curlicue around. But they also have the ability to just form these long sheets, what they're called the beta sheets. And those are the two main spatial arrangements that we talk about when we're talking about secondary structure. Okay, so first, I gotta know what order everything comes in. Second, I gotta know, does it curl up on itself like a helix, or does it lay flat like a sheet? Okay, and then number three is going to tell me, okay, now, once it's coiled up or once it's laid out flat, then what does it do? So if those coils curl on top of themselves, you could get this really exciting sort of wiggly looking thing. I'm putting a face right there because I'm not really sure how to describe it in layman's terms. But tertiary structure is like, okay, so we have everything in order. We know that the line, once it's in order, wants to curl up or wants to lie flat. And then once it does that, then what does it want us to do? It backs up one more time. All right, enzymes. Enzymes are proteins as well. Okay, so the amino acids make up proteins. Proteins can be enzymes. Okay? And enzymes are important because they speed up chemical reactions if they don't just carry it out to begin with, okay? This is what's also called in chemistry a catalyst. Catalyst, okay? And so what it does is it doesn't actually get in the reaction and say, come on, you guys, we've got to hurry. What it does is, we've talked about this before, we've talked about where you need to overcome the strength of those barriers. You need to overcome the forces that are holding it together, and the catalyst makes it that much easier. The enzyme makes it that much easier by doing some of the work ahead of time. Okay? All right. That's what it says right here in sciencey words. Lowering the energy barrier that must be overcome to go from reactants to products. Okay? We talked also about the conversion of hydrogen peroxide to water and oxygen. We talked about that extra oxygen escaping from solution. So that is catalase or hydrogen peroxidase. That's responsible for that reaction and for speeding it up. Also, this is a pretty cool thing. If you put a slice of potato in hydrogen peroxide, you're going to see bubbles form on the surface of the potato because the potato has water in it as well, and therefore has oxygen in it as well. So you will get this enzyme working to convert that hydrogen peroxide solution that you dropped it into, it's going to start breaking it down into water and oxygen. Okay. So this says a molecular model, which means that it's something that's more accurate in the sense of exactly what it might look like. But let's look at the schematic model. Okay, when we have an enzyme, it has this little, like a parking spot right here. Okay, and see, it's exactly the same shape as this substrate. Okay, so the parking spot is called the active site. The substrate fits exactly in. The enzyme does its work, and then it releases the products. Okay, so the substrate comes, parks in the spot, and then once it is broken down appropriately, then it flies off in its constituent parts to go to the next part of its reaction. Also, there are coenzymes. and that's something that helps an enzyme. That makes sense. Cooperation, right? Coenzyme. And so this is a lot of times where vitamins will be used. I don't know if you guys have heard this explanation, but like vitamin D will help your body utilize calcium better and things like that. We have lots of these cooperative processes in our body when they involve enzymes to, yet again, make it just a little bit easier for us to overcome what naturally goes on. Okay. All right. It has already been 20 minutes. I have had you guys for long enough. So here is where I'm drawing the line before nucleic acid. So this is going to be where we stopped on 4/7/20. All right. And I will have this ready and out to you, and I will have questions put forth in a questionnaire. And I hope you guys have a great and wonderful day.